Instead, we're working with sugar. Chemical formula looks a little bit more complicated, but our question here is how many molecules of sugar are there in a 2.25 gram spoonful? So if you, like me, are the type of person who drinks coffee every day, first and foremost, but in addition to that, likes to add a spoonful of sugar to your coffee just because it helps to, cut the bitterness a little bit, the average mass of a spoonful of sugar is 2.25 grams. So what we're looking for here is quite literally how many molecules of sugar, assuming that your sugar is just straight up glucose, which if you're buying, sugar at the store, either like raw sugar or processed sugar, it is all glucose. It's all just C6H12O6. So we don't have to assume any like averaging for a mixture. It's just straight up one compound. You have a spoonful of sugar. How many molecules are there? All right, so we've seen a couple of example problems like this already, so I encourage you again to see if you can't figure this out for yourself. There are actually two different things that we have to solve for here, so let me get you off on the right foot. First, we need to find the formula weight of our C6H12O6 in much the same way that we just found the formula weight for water on the previous slide. Next, we need to use that formula weight to figure out how many molecules there are. So these are the two things that you are meant to find. So try this out for yourself. See if you can't figure out this calculation. See if you're getting a hang for where these calculations are going, how they're set up. And we will check our answers together in a moment. All right, welcome back. Let us figure out what the formula weight of sugar is and how many molecules there are in a single spoonful of sugar. All right, so our formula weight. We can use our chemical formula, C6H12O6, to figure out what the formula weight of the entirety of glucose is. So we can see according to our chemical formula, we have 6 carbons, we have 12 hydrogens, and we have 6 oxygens. Again, the subscript that follows the element corresponds to how many of that element are present inside of the chemical formula. So we have 6 carbons, we have 12 hydrogens, and we have 6 oxygens. I'm just gonna parentheses these off to make it clear. We need to find the elemental symbol for carbon, for hydrogen, and for oxygen on the periodic table and use the atomic molar masses presented to find the formula weight for sugar. All right, so if we observe the periodic table to find where the atomic molar masses of the carbon, the hydrogen, and the oxygen from glucose are, we would see that carbon, which has an atomic molar mass of 12.01 according to your guys' periodic tables, and this is in grams per mole. Again, what's a number without a unit? Want to make sure we're including the units here. We're going to add to that 12 times the atomic molar mass for hydrogen, which is 1.008 grams per mole. And we are going to add to that 6 times the atomic molar mass of our oxygen, which is 16.01, or 00, grams per mole. I just literally looked up at the carbons up here and saw a 01 and they just wrote a 01. Oxygen is 16.00. All right, we're going to crunch the numbers then. If we're following significant figures, this is the type of problem where we have multiple algebraic operations. And so I will freely admit I'm not a huge stickler for significant figures. If you're in the right ballpark for where the sig figs should be, you're fine. However, let's just break down the problem and see if we can't figure out what the sig figs should be. Well, the 6, the 12, and the 6 are all perfect integers. Right, they're counting numbers. They're how many of the element we are working with, so they don't count. So after the first multiplication, or the first round of multiplications, right, 6 times 12.01, 12 times 1.008, and 6 times 16.00, each of these numbers will have 4 significant figures present. And each of those 4 significant figures then will end up being present out to the hundreds place. So because each of these significant figures after the first round of multiplications are out to the hundreds place, coincidentally, just because of how that multiplication worked out, we want to keep 4 significant figures. At the addition step, again, we want to make sure that all of our significant figures are out to the hundredths place, just to emphasize it's after the decimal point. We're out here because that second algebraic step is addition. So it's the decimal place that's going to matter there. So the atomic molar mass that we are going to write out with proper significant figures is 180.16 grams per mole. All right, so again, I'm not a huge stickler for significant figures, so if you saw that each of these numbers have 4 sig figs and you instead wrote out 180.2 instead of 180.16, it's fine. You're close enough, right? We're just learning about sig figs at this point. If you want to follow step by step and get really good at it, technically speaking, if you're that type of like detail-oriented person, I'm not going to stop you. I mean, you should be striving for reporting your answers in proper significant figures. I just want to disclaim and say, like, in this stage while you're learning, I'm not going to be marking off a huge number of points because the number of significant figures is like off. You're fine. All right, so now that we have the molar mass for our sugar, we can use the molar mass, starting again with the mass that we know, to calculate how many molecules of sugar there are in that spoonful. That's been the goal. So we're going to start with what we know, the 2.25 grams of C6H12O6. We're going to multiply this by the form of the molar mass that is going to get us out of the unit of the gram and into the unit of the mole. So we want to make sure that grams are down below, so grams cancel, and the mole is up on top since that's the direction we want to move into. We can see, again, just to reiterate, we're like finding patterns here, we're finding clues. The 180.16 is with the gram, so that should be true when we're setting up our conversion factor as well. The 180.16 should be with the gram, which means it should be in the denominator. The number in front of the mole here is just a number 1. We are going to multiply this then by, again, the version of Avogadro's number that is going to get us out of the unit of the mole and into the unit of the molecule. If we observe Avogadro's number, the actual numeric component of Avogadro's number always goes with the something that we're trying to like work with. Not the mole's always there, but like atoms, molecules, moles, eggs, whatever the situation is, 6.022 times 10 to the 23rd molecules per every 1 mole. So this is how we set up our conversion factors. The grams are going to cancel out. We can see in the second step then, moles are going to cancel out since we have 1 in the numerator multiplied by 1 in the denominator, totally canceling out. We are left only with the unit of the molecule. All right, and I'm kind of running out of space, but I do have enough space down here in the corner to write what our answer is, which is going to be 7.52 times 10 to the 21st molecule. There we go. In fact, I'll even just write it up here on the top of the slide just to make it really clear. 7.52 times 10 to the 21st molecules. Right, so that is a 752 followed by 19 zeros, and that's how many molecules that we are, on average, working with when you have a spoonful of sugar. So again, it's just astounding that based off of a simple mass measurement, we have the most like rudimentary tools at our disposal, simple algebra, numbers that have been reported, standardized, given to us from those who have come before us, and we can calculate exactly how many atoms, how many molecules there are in a sample that we are working with. Like, it's extraordinarily mind-boggling if you allow yourself the time to kind of sit and realize the implications of the calculations we're working with. But if there is a reason that we have seen farther, it is because we are standing on the shoulders of giants, right? We are taking full advantage of everything that has come before us, and I think it's important to acknowledge that.